Hello and welcome to another day of Advent of Code. Today is day 12, I think, and today we're going to be navigating some ships. Let's jump into the problem to talk about what's going on. All right, so the input is a series of directions. I'm actually going to open up the parsing file to show you what it looks like. It's basically a direction or a command sort of thing with an integer after it, which is what we're going to call our unit. And each of these directions mean different things, and they mean different things in part 1 and part 2. But parsing this is pretty straightforward. Let's do the parsing, and then we'll talk about what it's supposed to mean for each part 1 and part 2. Because the parsing is pretty straightforward. So ret equals this. We're going to be building a list of tuples. I forgot to import the types. So I'll do that really quickly. But for line in s dot split lines, I'm just gonna split this. I just grabbed the first character out of this and used that as my direction. Direction equals line 0, and then the unit, which is the rest of the string, unit, or I guess we can call it like n, equals int of line 1 and onwards. So ret dot append direction n. Return ret, and so that should solve the parsing part. The parsing is pretty easy today, fortunately. Parsing. This is not defined. What do you mean it's not defined? It's right here. Oh, down here. Input S. There we go. Okay, parsed. Cool. So let's open up part 1. And most of what we're going to be doing is figuring out what these directions do and then handling them. And if we look at our description here, these directions are going to move a ship. The ship is initially facing east at 0, 0. So this told me two things. X equals Y equals 0. That gives us our initial place. And I'm going to represent the direction that the ship is facing by a tuple with the X direction and the Y direction. So if we're facing east, we can say that dx equals 1. So I'm going to say that east is... that way on camera. It's flip for me. So it's going to be in the positive x direction. Oops. And we're going to say that the y is 0, so it's not going upwards. So this way we can use this direction later. And let's see. We're going to loop over all of the instructions for direction n in input. Maybe input is a bad name. Commands. That seems like a better name, because input is a built-in in Python. So for direction and commands, we need to decide based on each of the different direction types. So there's north, east, southwest. Those are the easy ones. So let's do this first. If direction equals north, then dy plus equals, we're going to say that north is up. I actually made this mistake during my solve of this. For the first part, it doesn't matter whether you treat north as up or down. I apparently treated it as down because I was not thinking that straight, but I ended up fixing it in part 2. But anyway, dy plus equals n, if direction equals south, then dy, oh not dy, sorry, y plus equals n, y minus equals n, otherwise if direction is equal to west, then x minus equals n, otherwise if direction is equal to east, x plus equals n. Okay, but that solves the first ones, which is just move the ship normally. And then we get to the tricky ones, which is right and left. This is rotating the ship by that number of degrees. And actually, if we look at my puzzle input here, this is something that I made sure to check while I was running the puzzle, because I was hoping that they were all in 90-degree increments. Otherwise, we would have some problems here. And I ran... see, yeah, this is actually the exact command I ran. I ran grep -E LR across our input text and then sorted and uniqued it. And you can see that they are all multiples of 90, and so we can make some assumptions about how we're going to do our rotations. Basically, there's only going to be 4 possible orientations of our ship here. And the way that I chose to represent that is by a series of direction vectors, similar to what I have done here. Directions equals, and I put these all in order. So I started with north, which should be, let's see, I did y then x, but we're going to do x then y here. So north is 0, 1, and then I did east next, which is 1, 0, and then south, which will be 0, -1. So this is north, east, south, and finally we have west, which is going to be -1, 0. And so if I go forward in this list, we're going to go clockwise. West. And we'll use that while we're doing our right and left implementations. Okay, so otherwise if direction is equal to, and actually, let's see, x, y. I did y major because I was, maybe not thinking closely. But we're actually going to use this as a tuple form here. That way we can figure out what our current direction is and then change it. So let's say if direction equals L, we know that the number of turns that we need to do is equal to n divided by 90. We also know that if direction equals R, turns equals n divided by 90. So this will tell us how many turns left or right we need to do. And actually, you can turn left and right into the same thing by, if you go right 3 turns, that's the same as going left 1 turn. But I didn't do that simplification. I don't even know that it's actually a simplification. It makes the code shorter, but I think it's harder to understand. But anyway, we can figure out which direction we are, and if we need to turn left, we would subtract. Yeah, we would subtract our index in this. So if we are at index, 2, and we go left twice, we go up 2, and then we're going north. So that's how you turn 180 degrees. Whereas if you go positive 180 degrees, you go forward 2 indices. And so what I did with that is I did, and then, you have to worry about wrapping around. So if you're at the 3rd indice and you turn right once, you're actually going to wrap around and go north. So you go from west to north. So I use that by saying ship dir equals directions, and then I did directions dot index ship dir plus turns mod 4, because there are 4 directions. And so this is just like a reassignment of the directions here. And that's for turning left. Left, we add the turns? No, we subtract the turns for left. We add the turns for right. But yeah, oops. That's weird. Must press the wrong key. But we add the turns for right. So this is kind of how you manage the left and right. And then after we've done that, we do our last thing, if direction is equal to forward. And I usually like to have, an error for my unexpected case here. Unexpected, let's see, direction and n. That way it's easier to debug later. But for forward, what we need to do is figure out which direction we're going, and then multiply this by the n and add it to our x and y. So we can say x plus equals n times direction 0, and then y plus equals n times direction 1. And that should get us our answer there. And then the final part of this is the answer, and the answer is the Manhattan distance from the origin. And if you don't know what Manhattan distance is, it's basically if you were to travel blocks on, on streets in Manhattan, how far would you have to travel? So you can't do like diagonal distance. It's always like the integer number of units. And in this case, it's just return absolute value of x plus absolute value of y, and that'll be our Manhattan distance. And assuming I've written this all up correctly, this should give us 25 if I can spell. Direction. Oh, I made just one typo there. Unsupported operands for int and stir. Oh, we have 2 things. I meant to do shifter down here. Shifter 0 and shifter 1. And fix this bracket. And now we get 25. Okay, that is what we expect. So that's part 1. And if we're talking about algorithmic efficiency here, this is really, this is linear on the number of commands we have, and anything else in here is constant, so it's linear overall. This was a lot more of a reading problem, not necessarily a difficult one, in my opinion. But then let's talk about part 2. Part 2 is where it gets a little bit spatial and weird, and where you have to kind of think a little bit harder. I guess this was an interesting trick for part 1, so maybe I'm not completely discounting it. But let's look at part 2. And again, I'm going to rename this to commands. And I'm actually going to copy a lot of the part 1 code because we're going to be able to adapt some of this. So let's actually just take everything we had in here and do part2.py. So part 2 has a few different twists to this problem. Notably now there is a target beacon, and so that's what we're going to be moving with north, south, west, and east. And the R and L are going to rotate that target beacon around the ship, and then F is going to move the number of units of that target beacon. And I forgot to mention it here, but the target beacon starts at, oh, what was it? 10 east and 1 north, I think? I don't remember. I should double check. Let me double check. Otherwise, we'll spend a bunch of time building this and not have a good answer here. So spoilers, this has my code that I implemented. Yeah, okay, 1-0. Cool, or 110. All right, so if we look at part 2 here, we need to initialize that target beacon. So I'm gonna say, you know, beacon, actually they called it a waypoint. So we'll call it WY equals 1 and WX equals 10. And again, our ship still starts at 0, 0. We no longer have a ship direction. We just have this waypoint beacon and the ship beacon. For these, we adjust all of these to be the waypoints movement instead of the ship movement. And then we get to our rotation, and this is going to be tricky. We still need this turns count. We're going to still use that here. And then we're going to implement this in a second because I actually have to show you a diagram for how I thought about this, and kind of gives you some intuition about the math here. And then forward, the F is actually pretty straightforward. We're moving the X and Y in the direction of our waypoint however many times. So the X goes WX times N times, and the Y goes WY times N times. So this was relatively straightforward. But now I'm going to show you a diagram. So when we're thinking about a waypoint, we're really thinking about, our boat living here at 0, 0, and this is maybe our waypoint. So let's say that it starts at green here. If you're imagining one rotation around the central axis here, let's say it's counterclockwise. Let's say this is an L. We're going to travel over to here, and this is in our L. And it took me writing this out and looking at the points to realize what's going on here. But a rotation in the leftward direction is flipping the 2 coordinates and then multiplying the x1 by -1. So you can see 4, 1 becomes 1, 4, and then -1, 4. And that actually works in the next direction too as well. So you flip -1 and 4, and you get, oh, this should have said, there's a typo here. Dang it. It should have been -4, -1. There we go. So the -1 flips over, and then 4 becomes -4. So you have -4, -1. And again, if you flip this here, that works the same way. Now, if you're flipping in the other direction, so let's say we are starting at 4, 1, and we want to do a rightward turn, which we'll represent using orange, I guess, here. This is an R. In this case, we're still flipping the 2, but instead of multiplying the X, we're now multiplying the Y. And we're going to use that trick to do our turns here. So we computed the number of turns, 4i in range turns, and we are going to rotate our waypoint. So we're going to say WY, WX equals WX, WY. Since in both of these we need to do a swap of the Y and X. And then for left, what was it? Left, it was multiply the X. WX times equals -1. And for right, it was WY times equals -1 times equals -1. And so that's how I implemented the rotation part here. And if we run this, so that's right, part2.py, and we get 286. So, this one took a little bit of spatial thinking, but I felt that it was much easier than the previous problems. And again, if we talk about algorithmic efficiency here, this is ON, and even though we have a loop here, this loop is bounded by 3 or 4 turns, so it's not all that big. And if you really want to bound this, you can mod this by 360 because doing more than 360 degrees of a turn is the same as doing just a smaller turn. But anyway, hopefully this was useful, and I'll see you again for day 13.